Hi, welcome back. So we are in Chapter 6, Prediction by RCC, at the last unit of prediction from the start to the end. We have accomplished all what we need to actually understand concerning the map of prediction that we established from the very beginning of this course. So I hope now by the end we are able actually to establish our own framework once we start looking for right prediction model. I have decided, as I've said in the last session, to looking at something called feature engineering. And when we speak about feature engineering, actually, there are two important outlines I can think about it. The first one is a preparation for your data. And the second one, it's related to dimension reduction in case of having a large dimension of data. Now, to actually illustrate the idea of feature engineering, first of all, concerning the point of preparation of the data, I have this cartoon which represents just different type of data as x1, x2, x3, etc. And there are a few steps we have to take before we start talking about feeding these data into this map, either from the left or from the right. First of all, we know by now from the second book of this material, that is analysis from the start to the end. We have discussed different type of data in terms of nominal or ordinal or ratio data of values that x1 can take. In this particular case, it's a kind of a categorical with answer of yes or no. Maybe we can look at it from the perspective of a nominal. Why? Because there are two groups. We don't have specific like preference. How can we transfer this into coding perspective? I mean, we need to deal with numbers end of the day. Possible, or the easiest way to code this, it could be 0 and 1. For example, if I would say yes, code 1, and no, it code 0. You could also go with 1 minus 1 or any other numerical representation you would like to work with. X3 here, which is again have two possible categorical, so I could follow the exact same mechanism. But let's actually navigate and things get more interesting if we look at X4. Let's see what are the possible range of answers that we have got here. I could use the exact same mechanism by saying, well, the nurse is 0 and then 1 and then 2, but might you run into a problem, and the problem is that let's assume this x1 represent the feature that we're trying to predict. It's my y. If I would have to organize this, what kind of a classifier I could come up with and start to think of possible arrangement where I want the greens to be somehow separable. Well, it's obvious in this case that I cannot really rely on the idea of changing orders of the range or the outcome of this variable, I mean x4. To this end, why didn't I create here extension? If it is nurse, that will be active and these are zeros. If it is admin, well, the second will be active, the others are 0. If it's a doctor, 2 are active and the third is 0. The only things that you have to consider in this case that x4 now, it doesn't extend to be only 1, but we will have to add 2 more. So this will be x40, x41, and x42. So in other words, that we expand the dimension of this data set. Another case you might end up with is like the case of x5. Well, x5, it's obvious here to have a joint situation. One instance could have multiple of that. We could rely on the same mechanism here by saying, well, I got somebody has only pain, so it's going to be 1 and then 0 and 0. The other guy happens to have pain and plucker pain, so it happens to be 1, 1, and 0. And the last one actually have none, that means 0, 0, and 0. Another case of this x6 feature, which represent the age in this case. Well, I could easily here say, instead of using the mechanism of grouping of 40 years or 20 years, 50 years, maybe I could use some sort of decade. So every 10 years represent 1 decade. Now, another case, look at x2 here from a numerical perspective where we have like continuous kind of value. Maybe I don't need really to encode anything in here, but soon you will discover that we will have a problem. A graph of the data on certain scale will be affected. That's why we can look at something called standardization of the data. One of the possible way of standardizing data by taking every case of x1 and subtract it from its mean and then take that value and divide by its standard deviation. And the outcome of such operation will lead you to a value between -1 and 1. So in this case, all these x2 will be transferred into a value between -1 and 1 without losing their own intuitive meaning, as well as the x7. But the importance of feature engineering is to prepare the data set to look like this. Now, the next thing we want to talk about, it's related to dimension and reduction. In this case, if you would have a certain data set with a space of variable from x1, x2, x3, xn, and in this case, n could be a very large number. But you will find that from our discussion in the unit of You Must Know that dependency and independency are quite an important aspect, because some of the information might be redundant, so to speak. Having to know the value of x3 doesn't actually add much of the information, but x2 actually the essential one. We are looking for a way that we can reduce a dimension n to k, where k it should be, of course, less than n. We need a mechanism to show us the best set of features, x1 maybe with x5 and x10. They all together can be very powerful set of features, can really tell me something. Whereby some features like x2 and x8 doesn't really explain much. Explain what? This is the point where I have to reach the point of variation. And from the variance also we can extract another intuitive number we call the standard deviation, which is actually the square root of that. So it's a sigma or the S. But what I'm trying to say here, in many of the material I have seen that trying to speak about reduction of dimensionality using what's so-called the PCA or principal component analysis, which actually relies on the concept of variance. Very important to realize that. It actually drop out the fact of discussion that the variance relies on the calculation of the mean, and the mean relies on the calculation of taking the sum of the values. But how if one of these values were actually outliers? So we have to be very, very careful while we are actually trying to understand, rather than the steps of calculating PCA or whatsoever, or reducing dimension, but also to understand the consequence of picking up something wrong, and based on that wrong things that I have built up the entire thing. How about if I take x1 and x2 all together? Imagine if it's x1, I expect the mean here. Of x2, I expect the mean of here. So there is a point here where I expect all my points, but it is obvious to see this isn't the case. And in this particular measurement, we call it the covariance. It can indicate the relationship between them in terms of variability. And from covariance, actually, we can literally construct a matrix. So the diagonal, it represents every value of a variance, depends on value. Whereby it's a symmetric that x1 and its vary with x2 by how much. Now, it turns out this covariant matrix, it can be a very powerful matrix to help me reduce the dimensionality of n and reach to some kind of a k. How? As we discussed before, and a very important principle, and that is called eigenvalue and the eigenvector. And the idea here, these eigenvalues and these eigenvectors corresponding to each one of them, these values, it could be actually ascending in a certain order, which is I was talking just now here. I would love to reduce this n into a k number. Exactly the answer to what I'm saying. In other words, to say, well, it turns out with the largest eigenvalue, it tells me something more interesting. Now, more intuitively, I mean, this is the solution of the problem we were talking about just now here. But let me show you that visually. Now, the idea of eigenvalue and eigenvectors, I want to reduce this x1 and x2 into one dimension. I could choose a line. And when I say line, it's just a vector. I think you should be aware of that. And I will call it the x prime, we need to project every point, the original point, onto x prime, so to speak. Now, how to project? Once again, you could get back to our examples and remember projection, which basically I could pick up a perpendicular line here, and then I take every point as this is the origin, and then I start to project. I will end up with the point looks like this. Now, I want you to see carefully, that's why I drag these dash lines. The actual value of this point, which was a pair of x1 and x2, it become nothing but a single value of x prime, and so on and so forth. So we reduce the dimension as we achieve. But there is a very, very important things to recognize, and I hope you can see it quite clear here, these two red points. Now, in the original space of x1 and x2, you could tell me how much distance in the original space is a quite large distance I could consider. I have projected this point here, and I have projected this point here, and I want you to tell me how much distance do you see happens between them. Very, very small distance. Now, this distance can be explained by variance. I want actually to look for such a new x prime that actually maintain the reality of the distance between these 2 points. So if this is distance 1 in the real original space and this is distance 2, the difference between d2 and d1, it is an error. And this error need to be minimized. To minimize this value from derivative perspective, well, I know how to calculate d2, and I know d1 how it's been calculated based on x1, x2, x1, x2. Could consider this as a parameter and take the derivative of that. And then if I go to the original line of x1 and x2, and I capture the covariance between them, now this covariance collapses into a variance of x prime. This x prime line describe a certain variance. If I pick another line, this is another x prime. Let's say x prime 2. Now I do the same exact procedure. Now tell me the distance between them in the new x prime and the distance in the original space. Are they two different? You will see they are very, very close to 0. It means x prime 2 happens to be really, really better than x prime 1. One more thing, if you look at the entire variance of all the points here on this x prime 2, sum it up, it's absolutely going to be larger than the variance of x prime 1. Because you can see a small variance, here is a larger variance. It turns out, another word to say, if I choose a variance, the largest from its previous variance, this variance is absolutely what I am looking at, which represent, of course, the x prime or the new dimension. Or another word to say, if I'm looking at a prime or x prime, I'm looking for some x prime that the distance between the original and the new projection is as close to 0 as possible. So you look at it as a minimization problem in terms of distance, or maximization problem in terms of the variance is the exact same idea. And the procedure to do that, it turns out, of course I leave the proof for you to do that this x prime happens to be the eigenvector that we are talking about. That can be intuitively great because you will have two lambdas here. You will have lambda 1 correspond to x1, lambda 2 correspond to x2. And each one of them, of course, have its own vector. Which one of them have the largest lambda, it's perfectly better than the other. By the way, before I just end up with this session to tell you, if I have number of these eigenvectors, recognize which one the best of them. For example, this might correspond to x prime 2, and maybe the other one correspond to this guy. It's another vector, but very close to it. But this one was completely arbitrary. Justify which one is the best for you to pick. Now this is called PC, or a component. Now, how to do these procedures, I have just actually laid down the framework, and you should be able actually to follow the logic. So the simple step that I can follow, first I can standardize the data sets. The second thing I would love to do is to capture the covariance, and then I can capture maybe the eigenvalues and corresponding eigenvectors of each one of these values. And finally, I can put them in ascending order. I could pick how many components I like. One dimension explain maybe like say 60% to 70% of the variability on the original. The second one maybe explain 5% and so on and so forth. But the sum of all of them must actually come to 100% anyway. Let's go ahead and implement this simple example on Python where step by step we can look at this. Where we have a data set here, it had just 150 instances by 4 different values. So we have x1, 2, 3, and 4. And I picked like 4 to be easy to visualize later on with 2. So the first step I wanted to do just to make a standardization for the original value. So here we have now all the values have been standardized between -1 and 1. This is the first step as we said. So now I have one instant with x1, 2, 3, and 4. So 4 features. And I would love to reduce these 4 into only 2 features. By the way, maybe I missed to say, these 4 features, it has also a y target. So let's look at the y here. We have 0, 1, and 2. So we have 3 different classes. In other words, to say each one of these, it could have a class of 0, 1, or 2. Anyway, so to get back to the task here, if I want to pick feature against every other combination of the features, it means I will have like n-1 factorial possible combinations. So in other words, here I will have 6 because 3 factorial. So I have to take this against 1, 2, and 3, then this against 2 and 3, then this against the 3. So 6 different combinations just to keep looking. How about if the dimensions I can measure like 100? Impossible to do that manually. That's why PCA could really be intuitively great. I wanted to show you some of the ideas here. So I have just graphed the data here. Let me show you actually against each other. So this is x0 against x1. I could maybe change here x0 with x2. And you could keep looking at them and see which one is more intuitive than the other. So I just wanted to show you this before we start our procedures. Later on, we're going to get back here again and show you something more interesting. Let's capture the covariance. So again, I'm using just NumPy covariance. And now this is the variance of x1, variance of x2, 3, and 4, the diagonal. And it's obvious the variance have to be unified around 1 because we have standardized the data. If I capture the correlation and covariance were almost identical in values because I standardized the data. So what I can read from here, that the correlation or covariance between x1 and x2 obviously is negative. But you see with the 0 and 2 and 0 and 3, they're strongly correlated. So one of them is really dependent on the other. You could look at the others as well. Anyway, so this is my covariance matrix. Now I am ready to capture the eigenvalue and the eigenvectors. These eigenvalues in ascending order. You will see very obviously now how much each one of them contribute to the variation, in other words to say. So the first x1, it actually explains 72%. The second one is 22. And the third one is 3.66. So the variance starts to drop down massively. Now cumulatively, you could see this is 72 point combined with the second, 95%. So in other words to say, x1 and x2 together, it could give me 95% as if I am dealing with the original data set. So this is a real reduction of the dimension from 4 only to 2 dimension. Now you look at the actual projection of this point here and look at this point here. The distance between them that much. On this line, the distance again is that much. So this is a successful presentation using lambda 1. It shows you both of them actually were able to explain like almost 95% of all these, whatever their variation on this new line. Next thing we want to do, we can make a report to print actually each eigenvalue and its corresponding eigenvectors. And then I can create from here the component. For example, I have decided on 2. So in this case, I will pick the first vector and the second vector correspond to the largest eigenvalue. I need now to project all the points on this 2 vectors, right? Which is actually the eigenvectors in this case. So now I have a new 150 by 2 data set with only 2 dimensions. I will end up to see the actual presentation with principal component 1 and principal component 2. So you could see really by looking only these 2 components or these 2 variables, I could be able to actually make some interpretation from here. Now I hope by the end of this entire material that we went through the steps of this book prediction from the start to the end, you have come to a comprehensive understanding on the mechanism or the framework of prediction and how to use your own ability actually to design your own algorithms utilizing the existence of some other frameworks. And I hope by the end of this, you are able now to proceed further. Thank you very much. Hope to see you following the content of our next and last book of The Big Bang of Data Science.